We're going to continue naming, and we're going to add something called the stock system. So you learned how to name binary compounds and ternary compounds. I'm giving the stock system in the last part of these notes their own lecture, their own video, because the stock system is something that can be a little confusing at first until you get used to it. If you look at your periodic table, and we look here in the middle, these elements in the center of the table are called transition elements. And one of the things that's special about the transition elements is they only make positive ions, but many of them can make more than one type of positive ion. So when you look at, for example, iron shows up a lot. Iron can be +2 or +3. Now remember, these are possible oxidation states, so there might be more choices than just what you see listed here, but these are the most common ones. Manganese, +2, +3, +4, +7. And if we make a compound with iron and oxygen, binary compound, FeO or Fe2O3 are going to be two different compounds, but their names would both be iron oxide. And we need a system for letting people know which of the two compounds they are. They're going to have different formulas. They should have different names, but with the binary rules, they would end up with the same name. So we added something called the stock system to those rules. And the stock system is going to be used when we are working with atoms that have more than one positive charge. So let's look at the examples in your notes first. Iron 2 oxide or iron 3 oxide. So two different names. When we form the compounds, we're going to look up what element it is that's iron. So iron is Fe. And this Roman numeral always goes with the positive ion. So this 2 applies to the iron. And what this Roman numeral is telling me is the charge. The Roman numeral tells you the charge on the ion. The Roman numeral tells you the charge of the ion. The Roman numeral tells you the charge. It's in parentheses. It goes with the positive ion in front. It doesn't tell me how many. It tells me the charge, and it's always telling me the positive charge. So if this is iron 2, that means I have iron +2, Fe +2. If this is iron 3 oxide, I have Fe +3. So Fe +2 or Fe +3. They both end in oxide. If we look at our periodic table, the only charge that oxygen can be when he's negative in these types of compounds is -2. There's going to be very few exceptions to that. So when we put the particles together, remember we're using least common multiple because we want our compound to end up neutral. So if I have one iron at +2 and one oxygen at -2, the least common multiple between 2 is 2. So I need one piece of iron at +2 and one piece of oxygen at -2. And if you add those charges up, +2 and -2 gives me a total charge of 0. And so that would be the formula for iron 2 oxide. Iron 3 oxide, iron has a charge of +3, oxygen's -2. The least common multiple between 3 and 2 is 6. So I need 2 irons at +3 each to get a total positive charge of +6. And I need 3 oxygens at -2 each to get a total negative charge of -6. And this way the total charge would be 0 and I would have a neutral compound. So these numbers become my subscripts. the number of positive +3 iron ions I need to get my least common multiple of +6 is 2, so Fe2. The number of negative -2 oxygen ions I need to get my least common multiple of -6 is 3, so then it would be O3, Fe2O3. Very similar names. The only thing that's different is the Roman numeral. The Roman numeral is telling me the charge on the positive ion. Your total compound has to have a charge of 0. Very different formulas. Iron 2 oxide, just FeO. Iron 3 oxide, Fe2O3. Let's look at the lead examples down here. We have lead thiocyanate, we have lead 4 thiocyanate, and lead 2 thiocyanate. So we're going to split these compounds at the lead 4 and the lead 2. If you look on table S, the symbol for lead is going to be Pb. So Pb is the symbol for lead. This Roman numeral tells me the charge of the lead. So I have Pb plus 4 in the lead 4 thiocyanate and Pb plus 2 for the lead 2 thiocyanate. Thiocyanate does not sound familiar. It doesn't end in IDE, so it's probably not an element. So the first place I'm going to go is table E to see if it's one of my polyatomic ions, and here it is. Thiocyanate, SCN with a total charge of -1. So thiocyanate, SCN with a charge of -1. SCN -1. SCN -1. Okay, so again, our goal is to make our compound have a total charge of 0. So what's the least common multiple between 4 and 1? Least common multiple between 4 and 1 is 4. So how many leads at +4 each do I need to get a total of +4? And how many thiocyanates do I need at -1 each to get a total of -4? This is the kind of algebra that you're doing in your head when you form these compounds. So to get a total of +4 charge, I need one of these +4 leads. So I write that as Pb. And to get a total of -4, I'm going to need 4 of these thiocyanate groups. Now you have to be really careful, because if you have your thiocyanate and you just put a 4 right here, what that means is 1 sulfur, 1 carbon, and 4 nitrogens. And that's not what we want. In order to show that you have 4 of these groups, you need 4 sets of thiocyanates. We're going to have to put the thiocyanate in parentheses. So then what that means is that you have 1, 2, 3, 4 sets of that polyatomic ion. So when you write this compound, it's going to be Pb parentheses, SCN, end parentheses, subscript 4. For the lead 2 thiocyanate, it's going to be the same math, but instead of +4 here, you are trying to get to a least common multiple of +2. So for every 1 lead, you're going to need 2 thiocyanates. So again, very similar names, but different compounds with different formulas. You're not only going to have to write the proper formulas from a name using the stock system, but you're also going to have to turn a formula into the correct name. So I borrowed a few examples from a website, and we're just going to go through and name them. So CUS. Now, one of the things that's difficult is at first it's going to take you a while to know whether you need to use a Roman numeral or not. If one of the squares on the periodic table for your positive ion only has one choice for a positive ion, you do not need to use a Roman numeral. If the square has more than one choice for a positive ion, you are going to need to use a Roman numeral. So if we look at the periodic table and we find Cu, Cu is right here, it's copper, and it has two choices, either +1 or +2. So we're going to need the Roman numeral. Okay, so now I say, all right, I have CuS. I know that CuS, the Cu is copper. I know I'm going to need a Roman numeral because it's either +1 or +2, and I don't know which yet. And the S is sulfur, so it's going to become sulfide. So now I need to figure out what charge the sulfur is. To figure out whether this copper is +1 or +2, so those are my choices, I need to figure out what charge is the sulfur. So I go back to the periodic table, and I find sulfur square, and sulfur, when he's negative, is -2, because my choices are -2, +4, +6. So the sulfur must be -2, and the copper is either +1 or +2. So then I have to do some algebra, and I have to think, well, I have one sulfur at -2, so my negative charge is -2. I know that my whole compound has to be neutral, so my total for the copper has to be +2. I have one copper because there's not a number there, so what must his charge be? Oh, he must be +2. Is +2 one of the choices? Yep. So this must be copper 2 sulfide. Okay, next on the list. So we got that one done. PbBr4. So Pb is lead. We just used that for one of our other examples. Make ourselves some room. Pb is lead. So PbBr4. I know it's going to be lead. I know from my other example that it's going to need a Roman numeral. And Br is bromine, so it's going to become bromide. I need my periodic table, and I need to look up lead and bromine. So lead is here. It's going to be either +2 or +4. And bromine, when he's negative, is -1. So lead +2 or +4, bromine -1. Don't know which yet. Bromine's -4. Okay, so then I do my scrap work. I have 4 bromines at -1 each, so that's a total of -4. I have 1 lead. I don't know what his charge is, but I know his total is going to have to be +4, so that equals 0. So this lead must have a charge of +4 then. So this must be my +4, and this becomes lead 4 bromide. If you don't know how to write the Roman numerals yet, make sure you learn Roman numerals up to about 7. Okay, let's skip down a little bit here. We're going to go to number 6. SN3P4. SN3P4. Okay, SN. If you don't know what that is, you're going to use table S and you're going to find it. SN happens to be tin. P is phosphorus, so this is going to become phosphide with the pH, phosphide. We're going to look at our periodic table and find tin and phosphorus. Phosphorus, and I drew over the top, so we're going to use our eraser to clear that out. Oh, -3. And tin, Sn, is going to be over here, and it's either +2 or +4. So +2 or +4, and phosphorus is -3. So tin +2 or 4, phosphorus -3. So I do my scrap work over here. I have 3 tins. I have no idea what their charge is. I have 4 phosphoruses at -3 each. So 4 times -3 is -12. If I want all of this to add up to 0, my positive charge is going to have to be +12. So if I solve for x, x is going to have to be +4. So this tin is +4. So this becomes tin 4-phosphide. Okay. I want to talk about the difference between 9 and 10 down here briefly, just to point something out to you about mercury. HGO. So HGO. Mercury is always going to have a Roman numeral in the middle of it. So this is going to be mercury something oxide. Oxygen is, except for a few exceptions, going to be -2. So without even using my periodic table, since there's one piece of oxygen at -2, this one piece of mercury must have a +2 charge, so this is mercury 2 oxide. That last one, Hg2F2. Whenever you see mercury as Hg2, be very wary of it. So fluorine is going to become fluoride. But take a look at reference table E. Every once in a while this shows up where Hg2 has a total charge of +2 and is considered a polyatomic ion, and they're going to call it mercury 1. Each of these mercuries has a charge of +1, but it's coming in a set of 2, like it's diatomic. So the total charge on that is +2. Doesn't show up very often, but if mercury 1 shows up, make sure you remember that it's there on your reference table. So this is going to have a charge of +2. Each fluorine has a charge of -1 because it's the only charge fluorine can be. So there's 2 of them. This guy has a charge of +2 total, so each mercury must have a charge of 1. This is going to be mercury 1 fluoride. Watch out for mercury. That's kind of a trick. Okay, so stock system, Roman numeral tells you the charge. It tells you the charge. It tells you the charge. It relates to the number of pieces. It will help you figure out the number of pieces, but it's really the charge of the particle. I cannot say that enough. That's the most common mistake. Last little bit for naming here. There are a few compounds that you're going to have to do common names for, and it's typically when you have 2 nonmetals together. So 2 nonmetals together, and things like carbon monoxide versus carbon dioxide. Now they could name these with the stock system, and this would be carbon 2 oxide, and this would be carbon 4 oxide, but for a lot of things we use this other naming system where you just state the number of negative ions. So the mono in front of the oxide means just 1, so carbon monoxide, CO. Carbon dioxide, the di in front of the oxide means 2, CO2. Things like carbon tetrachloride. That one shows up. It's a really poisonous solvent, but it does show up every once in a while. They'll talk about it. Tetra is 4. So carbon tetrachloride is exactly what it says. 1 carbon, 4 chlorines. So if you see a name for 2 nonmetals put together and you see prefixes in front of them, just read the prefixes. It'll tell you the number of pieces. There's a few common names like ammonia you need to know is NH4. So that was an example in the first section of naming lecture. Acids are on reference table K. So here are the acids. In hydrogen, chloride would be in its pure form. It's a gas. Once we make it an aqueous solution, we call it hydrochloric acid. This would be hydrogen nitrite in its pure form. When we mix it with water, it becomes nitrous acid. This would be hydrogen nitrate. When we mix it with water and it's aqueous, it's nitric acid. So you kind of see the pattern here. The acids that show up on your final exam are all listed. Watch out for carbonic acid. Check this out. CO2 aqueous. CO2 AQ. Remember, this AQ means mixed with water. So what this means is you have CO2 and H2O. And when we put them together, that's the same thing as H2CO3. So that is carbonic acid. This is what happens when they carbonate water to make your soda pop, and it's acidic and it rots your teeth and is bad for your bones, so drink water. Down here is another one that you should watch out for, ethanoic acid. This first way is the organic chemist way of writing ethanoic acid, CH3COOH. And ethanoic acid is going to be named using rules for organic chemistry. C2H3O2 is the inorganic chemist way of writing it. The H is the positive ion. That C2H3O2 was the acetate polyatomic ion. So as a compound, this one gets called hydrogen acetate, so commonly called acetic acid. When we dilute acetic acid in water, it's called vinegar. So vinegar is nice diluted acetic acid. All right, that's the big important topics for naming. Make sure you understand the SOC system. If you don't get it, come see me for help ASAP and practice naming. And if it doesn't click right away, just keep at it. It will click before the final.